Alright, welcome to this series of lecture videos on the central limit theorem. So the central limit theorem is really the backbone of inferential statistics, without which it would be impossible to calculate confidence intervals for the population mean or conduct hypothesis tests. So let's illustrate the central limit theorem. And let's first try to describe the theorem in simple words. So the central limit theorem is the statistical alchemy that takes any chaotic population and, through the power of repeated sampling, transforms those random averages into a predicted perfect bell curve. In other words, if you were to take many samples of size 50, so each sample has a size of 50, and you would calculate for each of those samples from the population mean, then even if the population from which you take those many samples is not normally distributed, the distribution of those many sample means will be approximately normal, with a mean of all those sampling means which is equal to the population mean. And of course you still remember that the population mean, or the sample mean, is an unbiased estimate of the population mean. And what we can also show is that the standard deviation of that sampling distribution, or another word for the standard deviation of the sampling means, is the standard error, that is equal to the population standard deviation over the square root of n. So that basically captures the idea: the greater is the sample from your population, the more representative it becomes. And if you take many representative samples, the standard deviation or the standard error of that sampling distribution is less prone to have an error. And that means that there is less variation in that sampling distribution. But let's go through an example step by step. So to the right you see a histogram from a population that is heavily skewed to the right. So we pretend that there is a non-normally distributed population that consists of 10,000 observations, and the population was constructed such that the mean is 10 and the standard deviation, the population standard deviation, is 14. So now let's turn to the sampling distribution. So next assume that we take 1,000 random samples of size 100 from the population. So we randomly select 1,000 times 100 observations, and for each sample we calculate the mean. So we calculate the average for each of the 1,000 sample means. And what the central limit theorem now shows is that the means of those 1,000 samples are normally distributed. And the mean of the 1,000 sample means is equal to the population mean. This is that the mean of all the samples, which is mu, and then subscript x bar, has to equal mu the population mean, which is 10. And the standard deviation of the sample means, which is also known as the standard error, is equal to the population standard deviation over the square root of n. So that would be 14 over the square root of 100, or 1.4. So now here you can see the sampling distribution of the mean. So what I did is I calculated 1,000 samples where each sample consisted of 100 randomly selected observations from the population, and then I calculated for each of those 1,000 samples, the mean. And then I looked at the histogram of that mean, and that histogram is shown here. And you can see that it's normally distributed, and the mean of 10 falls into that middle bin. So that should suggest that the central limit theorem is in fact true. Well, we didn't prove it, but we used a Monte Carlo simulation in order to verify it. But what I will do in the next video, I will go over that Monte Carlo simulation in more detail in Excel, and that should help to really get a good understanding of what the central limit theorem is. So I hope to see you in the next video.